So for my first challenge that I'll be attempting, I'll be doing the tree Huffman decoding problem from Hackerrank. This was the next suggested exercise given to me or sent to me by Hackerrank through email. I get a couple of these every day, and you can too if you subscribe to hackerrank.com. I actually did the interview on Hackerrank, and so that's why I found all these questions that you can do in practice. So anyway, let's get into it. Let's take a look here. So the Huffman coding assigns variable length code words to fixed length input characters based on their frequencies. More frequent characters are assigned shorter code words, and less frequent characters are assigned longer code words. A Huffman tree is made for the input string, and characters are based on their position in the tree. We add a 0 to the code word when we move left in the binary tree, and when we move right in the binary tree. We assign codes to the leaf node, which represent the input character. Right, so unfortunately I'm already somewhat familiar with the Huffman encryption thing, but hopefully that'll help us out. Input characters are only present on the leaves. Internal nodes have a character value of 0 or of that symbol, sigma, whatever. Just like that. No code word appears as a prefix. So nice thing with Hackerrank, I guess, is there's no constraints listed here. Or rather, the constraints are listed here, and you don't have to guess at them. So it looks like the objective here is to decode a string, and paste the decoded output. So it's 0 when we go left and 1 when we go right. Let's look at the input structure. Looks like we're given a root node and the string to decode, right? Yeah, we're given the string to decode and the root node. And so we're to print out the decoded value. Okay. So, let's see. The node is the frequency of this tree. So how is a tree made? So the most frequent characters are at the top, or they may not be at the top. They're leaf nodes. They're leaf nodes. More frequent characters appear above. And no prefix. Basically, no. Let's see. What is it? So left is 0, 1 is right. Alright, left is 0, 1 is right. Right is 1. What else we have? So we're gonna give, I guess, I guess I can try and solve the problem as if it were like this. I'll just copy this. ABACA, right? So just so I can see it, ABACA. And if I were to normally decode this as a human, let's see. We can just trace it. We'll trace the tree here. So not knowing this part, I'll just cover this part up. this has to turn into A B A C A. So this character is 0 0. This character is 0 1, and this character is just 1. I mean, I guess we can. Did we start at the right or the left? It clearly states that the prefix of a code is not another code. So, for example, if there exists, if one is a code, then there is no 1 0 or 1 1 or 1 star. Okay. So you get a really heavy tree here, right? That's what it says. That's basically what it says. Yeah, no code word appears as a prefix of any other code word. Alright, so yeah. Okay. That literally means this is a 1 character level, this is a 2 character level. Can you go 0 0 1? Oh, so the tree is gonna end up looking like. That's a pretty shitty tree. The 0 is gonna be extended all the way to the bottom left and then branching off by 1. You're never gonna have 0 1 0, 0 1, etc. It's gonna go here and then here, here and there, here and there. Oh, I should try and demonstrate that better because the mouse is not it doesn't display. So that means you would ever only get trees that look like this 1 0 and then 0 1 0 1 oops 0 1 because since it's 1, yeah, you can never start a thing. Well, I guess. Oh, for example, here, if you were to branch off this one here, this one, you would get either 0 1 0 1 0 or 0 1 1. But 0 1 is already a prefix, so it's not gonna work like that. All right. Now, so if I were to decode this string, I see that there's a 1, so that's got to be the most popular solution, or I mean the most popular letter, whatever it is, right? So and then here's another letter, and here's another letter, and here's another letter. Like so. Oh wait, although you... Well, that's a letter too. So this is a special case. How do I deal with this? I was gonna say, I was just gonna parse by, I was gonna split the string by ones, and then ignore any pre-printed zeros. But that's a solution that doesn't work. Well, I mean, that's only because you can have one element that's so the leftmost element is going to be all zeros. For example, here in the B1 node, that would be represented as this 0, but this would not be able to contain a value because it's not a leaf node. So there's only one left leaf node if there exists one. Yeah. So if there's a leaf node that's in the far left, then it's an all 0 leaf node. Otherwise, it's a right. So the first thing I'll have to do is find the deepest left node. Right. And if it's a leaf node, if it's a leaf node, it has a character value. Okay. Then if it's well, that's about it. Otherwise, it has no value. And now our decoding sequence should work. What we'll do is, if it has a left node, for example, we look for, we can break on either all zeros. So we start from the left, right? We read until we find a 1. If we read if we read the maximum depth zeros, then we know it's that other letter. And then we start again parsing. Alright, so here's the algorithm. Start with the leftmost bit, I guess. Let me go ahead and comment all this out. Start with the left. The first thing I do is find that deepest left node, and the algorithm starts with the leftmost bit. If we have then we iterate through the bits until we find a 1. We're going to actually count the number of zeros. Yep. Count the number of zeros in a row we find. If 0 count reaches deepest left threshold, then we reset counter and decode continuous zeros. Otherwise, if we find a 1, we use the number of counted zeros with a 1 and go right. So we'll need a we'll iterate the string through a code loop. We'll need a find deepest left. What did I call it? Deepest left threshold. Alright. Then we need a get get node value, like that. We'll pass it the number of zeros. Okay, so there we go. So there we go. We have the string. So like I said before, the loop start with the leftmost bit. So for integer I is equal to 0, I is less than s dot length, I plus plus. Actually, the first thing we have to do is find the deepest left threshold. You get to find deepest left. Pass it the root node. We call it integer. Yeah. Yeah. Find deepest left root. So I had a thought there. Just checking my algorithm in my brain. I don't think I should do that. Kind of stopped. It's gotta be constantly talking. Okay, so what's gonna happen in find deepest left? It's pretty simple. While root not equal null, what's the value here? Node has a character data value. I'm not sure what frequency is. Maybe that's actually useful. Probably not. I can't think of a solution using the frequency. I think my solution will work. I mean, I guess I could take some time, but this is a solution and I'm just gonna grab hold of it and keep on going on. So with the root node, we loop through the root node while it's not equal to null, setting the root is equal to root dot left, basically. Yep. Basically, we just keep on going until it's not, until it is. If root if alright, so we go all the way down. If root dot data, wait, if it is equal to null, that means the loop will break. And then if the root dot right is also not equal to null, then we've ended on a leaf node in which we can return the data. Oh yeah, we need a counter, don't we? Yeah. Levels. Go 0. Levels plus plus. Is that right? So that's 1 0. Oh no, that's 1 0. Right. Yeah. So if so when we hit the bottom, we can return levels. If it's not equal to null, then we just return 0. Okay, and then here's the other one. Alright, so there we go. Deepest left threshold. So now we're just iterating through the entry string, and iterating the entry string. What was I doing? Let's start. Iterate through the bits until we find a 1, right? While counting int 0 count 0. Yeah, it shouldn't matter. If the if s dot, or if s dot car at I is equal to 1, basically, then we have the string decode decode equal to decode plus this is going to be a decode method here. Oh, we have a decode method. Tree value. From, we'll pass it a 0 count. So we just get tree value. What is it? Car tree value. It's character, right? Yeah, character. Character tree value integer count, or yeah, levels, right? And we should be okay here. We shouldn't have to check anything due to the constraints. If oh wait, yeah. Oh, we got past the root node too. Node root. Come on, root. Then we just iterate through the list, going left for the number of levels, and then we go right one. While this is a finite for integer I is equal to 0, I is less than levels I plus plus. If levels equal 0, then we just go right. Otherwise, we don't do anything. Yeah. Yep. It's less than levels. Then you just say root is equal to root dot left. Should even check for that. Return root dot right dot data. Like so. Easy, right? Yep. Okay. Else 0 count plus plus. We gotta reset the 0 count. 0 count is equal to 0. Yes, this works because we consider the case where there's no left nodes, then it's all ones anyway, and you'll never hit that threshold. It's not the right one. This is the deepest left threshold. So this doesn't work. This does not work in the case that the deepest left threshold is 0. It's actually, well, if it's 0, because it's gonna catch on the first instance. So I need to check for the deepest left threshold only if the deepest left threshold is greater than, yeah, if the deepest left threshold is greater than 1 and 0 count is equal to deepest left threshold, or 0 count is greater than 1 and is equal to the threshold. Either way, that one works either way. Then we have to have a other method for thinking. Car left tree. Just say levels and the node root. And it should be the same thing as this, except for we return. We just go down the X number of levels, and then we just return root dot data, like so. Plus left tree value levels root else we just increase 0. Okay, that should do the trick there.